Hello everyone, I am Poulami Mukherjee from Indian Institute of Technology Bhubaneswar. The title of my poster is Thermodynamic Curvature of Charged Black Holes with AdS2 Horizon. This work focuses on the calculation of thermodynamic curvature at low temperature for charged black hole with AdS2 near horizon geometry and study the thermodynamic properties of system taking into account both semi-classical and quantum corrections. Thermodynamic curvature provides empirical information about the nature of microstructure of any general thermodynamic system. Positive value of curvature means repulsive interaction is dominant in the system, and negative value means attractive interaction is dominant in the system. Here, we start with Einstein-Maxwell theory in AdS+2 spacetime. This theory is known to have charged black hole solutions with Laplace function like this. For fixed potential ensemble, we get different types of behavior for chemical potential greater than 1 and chemical potential less than 1. So for large black hole branch, the curvature is positive and diverges at t equals to 0, which is denoted by this red curve. And for chemical potential less than 1, there is a crossover, which is denoted by this blue curve, and this crossover point corresponds to the Hawking-Page transition. So empirically, for the large black hole branch, the system behaves to have repulsive interaction, which gets stronger as t goes to 0. So now the low temperature limit is taken at fixed chemical potential. This low temperature dynamics was computed by Sachdev et al. So you take horizon radius at fixed chemical potential and expand it in temperature. Here RH is the zero temperature horizon radius. Now we can get all other first order corrected thermodynamic quantities by plugging in R0. At low temperature dynamics, entropy also gets an correction term linear in temperature, where this gamma is basically the specific heat of the black hole. Now, if we calculate the curvature with the corrected quantities and plot it, we see that it reserves the behavior at t tends to 0, but there is a crossover which was not there in the earlier calculation. This crossover happens partly inside and partly outside this shaded region, which is known as the Schwarzian region. But the story is not complete without the quantum corrections. The entropy gets corrected further by a logarithmic term like this. And if we repeat the computation, we see that the curvature does not change much, but in both canonical and grand canonical ensemble, it saturates at the value instead of diverging. So there is a crossover in grand canonical ensemble, but there is no crossover in canonical ensemble. So this red curve is for canonical ensemble and this blue curve is for grand canonical ensemble. Okay. Then, so if we try to find the crossover point now, it completely falls precisely on this shaded region, which is the Schwarzian region. So the idea empirically is that it captures the shift from attraction to repulsion dominated theory. I hope you enjoyed my poster. Thank you.